In this video, we'll be looking at polynomial and rational functions. Now, a polynomial function is a function that can be written in the form f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus so on and so forth plus a sub 1x plus a sub 0 or a sub naught, where the n is a non-negative integer. And this is called the degree of the polynomial. The coefficients which are the a sub 1, a naught, a1, so on and so forth up through a sub n are real numbers, with a sub n not being 0, right? The domain is the set of all real numbers. Now, a sub n is called the leading coefficient, and a naught is the constant term. Now, there are two degrees in particular that we're going to study in more depth. That is a polynomial of degree 1 and a polynomial of degree 2. We start with the degree 1 polynomial, which is known as a linear function. And so a linear function is simply a degree 1 polynomial. A linear equation in two variables is an equation that can be written in the form ax plus by is equal to c, where the a, b, c are constants, and a and b are both non-zero. The graph of this equation is a line. If the point x1, y1, and the point x2, y2 are 2 points on a line with x1 not being equal to x2, then the slope of that line is given by m equals y2 minus y1 over x2 minus x1, and that is sometimes written as delta y over delta x, also known as rise over run. Now the slope is measuring the steepness of a line, so it's how steep the line is, right? So for instance, a line like this has a smaller slope than a line like that. Now there are two forms of a line that is typically used. We have a linear function in the form f of x equals mx plus b. Then it's said to be in slope-intercept form. M is the slope of the line, right? And b is the y-intercept of the line. In other words, b is where the line crosses the y-axis. If instead it is given in this form, y minus y naught equals m times x minus x naught, it is said to be in point slope form. Once again, m is the slope of the line, and now x naught, y naught is any point on the line. Let's now look at an example concerning linear functions. We wish to find the equation of the line that passes through the points 5, 1 and 8, 7. So what we're going to do this is we're going to start in point slope form and use that to write it in slope intercept form, which is the commonly accepted form of a line. So first thing we're going to need is we're going to need the slope. And remember that is delta y over delta x. So it's rise over run. Right, so it's going to be 7 minus 1 over 8 minus 5. That is 6 over 3. So the slope is 2. What we now have to do is choose one of the points on the line. It does not matter which one. So we're going to use this point, 5, 1. All right, point slope form would then be y minus 1 is equal to 2 times x minus, 5, which is 2x minus 10. Solving this for y will put it into slope-intercept form. So this means that y would equal 2x minus 10 plus 1, which is minus 9. So the equation of the line is y equals 2x minus 9. We next look at the degree 2 polynomial, and these are known as quadratic functions. So a quadratic function is a degree 2 polynomial. That is, it has the form f of x is equal to ax squared plus bx plus c, where a, b, c are real numbers, and a is not 0. The graph of a quadratic function is what's known as a parabola. So this is what a parabola looks like. It has an extreme point, which is known as the vertex. So in this graph, it is right here. Right, remember, an extreme point is simply a minimum or a maximum. If the parabola opens upward, which is the case here, then the vertex is a minimum. If it opens downwards, in other words, if it looks something like that, this would be the vertex here, then that vertex is a maximum. The vertical line that passes through the vertex is called the axis of symmetry. So it's right here, or we could have, in this case, right here. It's always a vertical line through the vertex. The parabola is symmetric about this axis. Now, I've already seen the general form. The general form is this right here. So I'm going to rewrite it down here. If a is greater than 0, the parabola will open upwards. If a is less than 0, the parabola will open downwards. Now, a little bit later in this video series, we will see why this is the case. So why does it open upwards if a is greater than 0, and why it opens downwards if a is less than 0. Suppose that we want to solve ax squared plus bx plus c is equal to 0. In algebra, we saw how to do this. We could either factor or use what's known as the quadratic formula. Here, we will actually go ahead and derive the quadratic formula or the quadratic equation. This is done by completing the square. So we start with ax squared plus bx plus c is equal to 0. Divide everything by a. Now move the constant over. We can now go ahead and complete the square. So remember, to do that, we look at the coefficient of x, we halve it, and then square, and add that to both sides. If we go ahead and now simplify what's on the right-hand side, we'll be left with b squared minus 4ac all over 4a squared. Now, the whole point of completing the square was that we could write the left-hand side of the equation in this form: x plus b over 2a quantity squared we now have to take the square root. Remember, when you take the square root, it's plus or minus. Now that can be simplified to have plus or minus square root of b squared minus 4ac over 2a. Now we can solve for x. X would then be negative b over a plus or minus the square root of b squared minus 4ac all over 2a. I'm sorry, that should have been negative b over 2a. Right now we have a common denominator, so we can write this as a single fraction. Negative b plus or minus the square root b squared minus 4ac all over 2a. I'm going to rewrite it so I can box it. This was the quadratic equation, or the quadratic formula. Now recall that the axis of symmetry is the vertical line that passes through the vertex. Well, the vertex is going to be halfway between the x-intercepts. Right? Why is it halfway? Because the axis of symmetry is perfectly symmetrical. Oh, I'm sorry, the parabola itself is perfectly symmetrical about this axis. So to find a formula for the axis of symmetry, we want the midpoint between the x-intercepts. And remember, to find midpoint, we just take the average. So the two x-intercepts are going to be given by this right here, the quadratic formula. So the first will be negative b minus the square root of b squared minus 4ac all over 2a. Then we add to it the second x-intercept, which is negative b plus the square root of b squared minus 4ac all over 2a. Then we take that and divide it by 2. Now if we look at this, we have a negative square root here, we have a positive square root there. Those two values will wind up canceling out when you add them together. We get a negative 2b over 2a, which is just negative b over a. That is all over 2. And so that winds up being negative b over 2a. So the axis of symmetry has the equation x equals negative b over 2a. There is a second form in which we can write a quadratic function, and that is called the standard form. And it is f of x is equal to a times x minus h quantity squared plus k, where the point h comma k is the vertex. Now, writing a quadratic function in standard form is useful for when we are trying to sketch the graph of the function. We will now go ahead and compare the standard form of a quadratic to the general form of a quadratic in order to find an equation for the vertex. So a times x minus h quantity squared plus k would have to equal ax squared plus bx plus c because they represent the same quadratic function. We go ahead and expand out that term on the left-hand side. We get a times x squared minus 2xh plus h squared, then plus k. That would have to equal ax squared plus bx plus c. We can now distribute that a through. If we compare the coefficients of the x terms, we find that negative 2ah has to equal b. We can solve for h and say that h is thus negative b over 2a. Now, that makes sense, right? Remember, we showed that x equals negative b over 2a is the equation of the axis of symmetry. What we now want to do is compare the constant terms. Doing that, we get a h squared plus k has to be equal to c. Solving for k, we get k is equal to c minus ah squared. However, we just said h is negative b over 2a. So this becomes c minus a times negative b over 2a quantity squared. That is c minus a times b squared over 4a squared. And finally, simplifying that, we get that k is equal to c minus b squared over 4a. And so, the function f of x equals ax squared plus bx plus c has vertex at hk equals negative b over 2a comma c minus b squared over 4a. So if we're given the general form of a quadratic, this is how we find the vertex. Let's now look at some examples with quadratic functions. All right, we want to first sketch the graph. F of x equals negative x squared plus 5x plus 3. Now, the first thing we notice is a is negative 1, b is 5, and c is 3. Right? Since a is negative 1, this means it will open downward. All right, let's now go ahead and find the vertex. Right, so remember the vertex is negative b over 2a. So it'll be negative 5 over 2 times negative 1, comma, then it'll be c minus b squared over 4 times a. The x-coordinate will be 5/2. The y-coordinate, we're going to have 3 minus, should be plus, 25 over 4. And this will simplify to the point 5/2 and 37/4. Let's find the intercepts now. So to find the y-intercept, we just plug x equals 0 into the function. And doing so, we easily find that the y-intercept is at 3. To find the x-intercepts, we solve f of x is equal to 0, so we can use the quadratic. We get -5 plus or minus square root of 25 minus 4 times -1 times 3 all over 2 times -1. This is -5 plus or minus the square root of 25 plus 12, which is 37, all over -2. So all of our intercepts, 0, 3. Now I'm going to use decimals here, 5.54130 and negative 0.54131, 0. Right, the idea of using the decimals here is to give us a better idea of where the point is actually located. We can now use all of this information to go ahead and sketch the graph. So we know it opens downwards. The vertex was at 5/2 and 37/4. Right, so 5/2 is 2.5. Let's say 2.5 to be located here. 37/4 is almost 10. Let's say it's right up there. There's the vertex. It crosses at -1/2. So let's say that's probably right about there. At just about 5.5. That's going to be like right about there. And it crosses the y-axis at 3. Now remember, this has to be almost 10. Let's say that's 10. Oh no, let's say 3 is right about there. That's terrible. Alright, so, I don't know, something like this. And it's good enough for government work. Right, if we go ahead and look, come over, let's go to the graph. Right, so f of x was -x squared plus 5x plus 3 . All right, let's change our window. Let's make it negative 10, positive 10 instead. And there we go. Here's our second example for quadratic. Projected assets of the Social Security Trust Fund, which is measured in trillions of dollars, is given by this monstrous looking function here, where t ranges from 0 to 23. T equals 0 corresponds to the year 2010. First, baby boomers turned 65 in 2011. We are going to find the assets of the Social Security Trust Fund at that time. So let's start with that. So for the year 2011, that corresponds to t being 1. Okay, so what we're looking for is a of 1. Now, I'm going to show an easy way to evaluate this. So if we come over to our calculator, all right, let's come back here. Let's first define our function. All right, so our function is a of t is defined 0.0008140t to the fourth. Then it was minus 0.0004333 t cubed plus 0.0001305 t squared plus 0.02202t plus 2.612. There's our function. Right, now it's stored. Now we just want a of 1. Hit enter, and it's 2.63, so on and so forth. We'll just say 2.63. But remember, a is measured in trillions of dollars. So this is $2.63 trillion. So in context of our problem, there were $2.63 trillion in the Social Security Trust Fund in 2011. Now the last of the baby boomers will turn 65 in 2029. What will the assets of the trust fund be at that time? So the year 2029. Corresponds to t equaling 19. So what we're looking for is a of 19. Now what we do is we go back to our calculator. Let's find now a of 19. And that is about 1.13. So $1.13 trillion in 2029. Finally, we're going to use the graph to estimate the year. All right, so I can delete that y there. Estimate the year in which the current trust fund is projected to go broke. Let's come back over to the graph. tab up. So delete this function here. Now, since I already have a defined, I'm just going to type in a of x here, and it should give a graph of a of x. There it is. We are going to have to adjust the window quite a bit. I want window, so let's adjust window settings. Obviously, we can't have t less than 0, so 0, and t goes to 23. However, I'm going to go a little bit further out than that. Let's go to 30. Y scale. Let's set this -2 to 2. Never mind. Menu. Window. Let's try -5 to 5. Alright, that's better. So to estimate the year in which the fund will be completely depleted, we're looking for where it's crossing the x-axis. Right, so it's somewhere here. So we want a value. So we come over to menu, we want to analyze the graph. We're looking for zeros. We're going to have to put in bounds. All right, so I know this is the 0 I'm looking for, so let's put the lower bound here. Let's put the upper bound here. And we get t is 23.5. So round that down to t equals 23. So a of t equaling 0 corresponds to t being approximately 23. And that corresponds to the year 2033. So if this projection holds, it is projected that the Social Security Trust Fund will run out of money in the year 2033. Now we turn our attention to rational functions. A rational function is any function of the form f of x equals n of x over d of x, for d of x not equal to 0, where n of x and d of x are polynomials. And the domain of rational functions is the set of all real numbers such that d of x is not equal to 0. We conclude with one final example. Study of driving costs based on a 2012 medium-sized sedan found that the average cost in cents per mile can be modeled by this function, where x, which is measured in 1,000, denotes the number of miles the car is driven in each year. We will use this model to estimate the average cost per mile of driving a 2012 medium-sized sedan 8,000 miles and 18,000 miles per year. So for the 8,000 miles, this corresponds to x being 8. So what we're looking for is c of 8. So if we come to our calculator, first we want to define our function. So c of x is defined as 1910.5 divided by x to the 1.72, all plus 42.9. Let's store that. Now let's find c of 8. That's about 96.3. So if we drive at 8,000 miles a year, average cost is 96.3 cents per mile. 18,000 miles corresponds to x being 18. So what we're looking for is c of 18. And that was about 56.1 cents per mile. Right, and that concludes this video on a review of polynomial and rational functions. In the next video, we will be reviewing exponential and logarithmic functions.